We want to prove that cis theta cis phi is equal to cis theta plus phi without assuming this. Cis theta cis phi is cos theta plus I sine theta. Cos phi plus I sine phi. Expanding, that gives us cos theta cos phi plus I sine phi cos theta plus I sine theta cos phi. Take away sine theta sine phi. Gathering the real parts gives me cos theta cos phi minus sine theta sine phi, and then we have sine phi cos theta plus sine theta cos phi. Now we should recognize this as being cos theta plus phi, and this as being sine theta plus phi, and therefore that is cis theta plus phi. By considering 5 plus I to the 4, 1 minus I, or otherwise, we want to prove this expression. So let's consider the 5 plus I to the power 4. So if we just look at it as a complex number, 5 this way, 1 this way, this would be root 26, and this is theta, and theta would be the inverse tangent of 1/5, which is a good sign because we've got that here. So this complex number here would be root 26 cis inverse tan 1/5. If we now consider the 1 minus I, 1 and 1, this is root 2, this would be pi by 4, so this one is root 2 cis negative pi by 4. So 5 plus I to the 4, 1 minus I, would be 676, which is root 26 to the power 4, cis 4 times the inverse tangent of 1/5 multiplied by root 2 cis negative pi by 4, which gives us 676 root 2 cis 4 times the inverse tan of 1/5, take away pi by 4. Now let's come at this another way by expanding this. Now we can use the calculator to do this, just need to make sure that we're in complex mode. And if we go to complex, there's a C expand function, and we'll just put in there 5 plus I, it has to be this I here, to the power 4, and we'll multiply that by 1 minus I, and we get this, 956 plus 4I. If we consider that, then this is 4956. If we do the square root of 956 squared plus 4 squared, we do find that we get 676 root 2, but this time it's cis inverse tan of 4 over 956, which is the same as 1 over 239. And therefore these two arguments must be the same. For inverse tan 1/5 take pi by 4 is equal to inverse tan 1 over 239, and then to get what we want we just need to move the pi by 4 to the other side. This final part is quite tricky and just relates to something that's actually on the formula sheet. If we do mod z1 minus z2 squared, that's actually equal to mod z1 squared. Take away z1 z2 bar, take away z1 bar z2 plus mod z2 all squared. If we do the same for z1 plus z2, then it's the same but with pluses in the middle here. So if we put these expressions equal to each other, then we can say that mod z1 minus z2 squared is the same as mod z1 plus z2 squared. So that's putting these equal, and then we can see that these would cancel. So what we have is negative z1 z2 bar, take away z1 bar z2 would be equal to z1 z2 bar plus z1 bar z2, and bringing everything to one side, that gives us twice z1 z2 bar plus z1 bar z2 is equal to 0. Now, once again, something from the formula sheet, that z1 z2 bar, the conjugate of that is the same as z1 bar z2, and therefore what we have is a complex number being added to its conjugate, giving us 0, and that means that the real parts must be 0, or the real part of this one must be 0, because it would be equal to the real part of this one. So therefore real z1 z2 bar is equal to 0. z1 we know is cis theta, z2 is cis phi, so z2 bar would be cis negative phi, and then z1 z2 bar would be cis theta take away phi. Now remember that this is cos theta take away phi plus I sine theta take phi, and since we know the real part is 0, that tells us that cos theta take away phi is equal to 0, and one solution to that is that theta take phi is equal to pi by 2. Another one is negative pi by 2, so if we put a modulus around there, that does the trick.